Hi everyone, my name is Federico. Today I'll be presenting Transcending Transcend, revisiting malware classification in the presence of concept drift. This is joint work with Feargus Pendlebury, Fabio Pierazzi, and Lorenzo Cavallaro. So we all know the story of machine learning effectiveness. So machine learning dominates in image classification tasks, in natural language processing tasks, in machine translation tasks. And while we've seen promising results in malware classification, there still seems to be something missing. So what's happening? Maybe we're just not ready yet. Well, while other domains treat adversarial attacks and adversarial behavior as a special case, in security everything is adversarial and always has been. So a detection system is worthless if it's not robust to these adversarial interactions. So whenever we deploy a new detection system, this triggers an immediate response from the adversaries, and sometimes this can be even quite extreme. And this is a nightmare for machine learning practitioners and researchers because it leads to a variety of dataset shifts. So this could be a covariance shift, prior probability shift, and concept drift. So these violate the core assumption of most classification algorithms that the training and test data are IID. In this talk, we'll be using concept drift as kind of the umbrella term for all these shifts. So this is the kind of problem that our lab was trying to address in Transcend, which was presented at USENIX in 2017. So Transcend adds to, so imagine this is the normal classification pipeline. You have a new example and an underlying classifier that's making classifications. Well, we add a couple extra steps to this. So first we have a conformal evaluator. So this is powered by conformal prediction theory and is responsible for sending a quality measure to identify examples that are drifting. And then these quality measures are then passed on to Transcend, which is a thresholding mechanism which then either accepts or rejects these predictions. So this is a classification with rejection. So on top of predicting, say, if an element is a cat or a dog, we would also have a kind of a third class you could think of, which is a rejection flag. So if this is true, then we actually don't trust the classifier. So in some sense, this pipeline with Transcend is recognizing that the classifier is imperfect and trying to actively remedy this. So our contributions in our work are the following. So the original Transcend performed extremely well, but we kind of identified some things which we wanted to really improve on. The first is a missing link between the conform prediction and conform evaluation, we use this missing link and this motivation to explain why conform evaluation is so successful. On top of this, using these kind of new theoretical insights, we develop new sound and more flexible conform evaluators and faster thresholding. So this is an effort into making conform evaluators actually usable in practice and scalable. And on top of this, we also evaluate on kind of different malware domains, so Android, Windows, and PDF malware, and we try different classifiers, so SVMs, random forest, and GBDT. So let's talk a bit about conform evaluators, and again, conform evaluators are based on conform prediction theory. So the conform evaluator is essentially the statistical engine that drives the rejection mechanism, and it's based on conform prediction theory, which is a method for providing predictions that are correct with some level of confidence. So and guarantees. So in typical operation, given a trained model, a new example, and a significance level epsilon, a conform predictor produces a prediction set that is guaranteed to contain the correct label with a confidence 1 minus epsilon. And this is importantly true only when we have two assumptions or two conditions, so that of exchangeability, which is generalization of IID, and a closed world assumption. So if we are testing on or training on cats and dogs, at test time we won't have a parrot, for example, or a random noise, let's say. So to calculate this prediction set, the conform predictor relies on the notion of a non-conformity measure, or an NCM, which is a function that's derived from the underlying classifier. So this is used to generate scores which represent how dissimilar each example is from previous examples of that class. So conform prediction and conform evaluation, for the matter, are completely classifier agnostic to the underlying algorithm, so we can look at a variety of examples of NCMs with different classifiers. So if we focus, for example, on the top left most, so the SVM polynomial case, the blue area highlights all the points which are less similar than the red testing point with respect to the black class, as defined by as induced in some way by the non-conformity measure. So then what we can do is we can quantify this similarity by calculating p-values. So this is the ratio of less similar points, so points in the blue area, to more similar points in the white area, but this is done in a label conditional manner. So we compute p-values for the two classes in this case. So you could imagine one class being, for example, malware, and the other class being goodware, and then we compute a p-value for both. So a p-value for the malware class and a p-value for the goodware class. So recall that conform prediction produces a prediction region given some sort of significance level epsilon, and you can imagine these prediction regions as being nested, such that the higher the confidence label, the more labels, or sorry, higher the confidence level, the more labels will be present. So and kind of as edge case, so a prediction region containing all possible labels may be produced for an epsilon level of 0. So with an epsilon level of 0, we're saying essentially with probability 1 minus epsilon, give me true. I want the label to be in the label set, but now 1 minus epsilon is actually just 1. So I'm saying with probability 1, what's the give me a prediction region that contains a true label, but now by the closed rule assumption, we know that the label has to be contained in the label space, so we're just outputting the entire label space. Now instead, the other edge case is when epsilon is 1, and this is we output an empty set, because here we're saying with probability 0, give us a prediction set, or give us a prediction set that with probability 0 contains the true label of the sample, but then again we know that this is impossible, because by the closed rule assumption, again, we know that the true label has to be contained in the prediction set. So this is kind of a contradiction. Of particular interest is also the region containing a single element, and then this is kind of sandwiched by the confidence and 1 minus credibility. So we can compute the credibility and confidence scores based on the p-values we calculated, and these confidence and credibility scores will become quite useful. So this is kind of the key intuition that connects conform prediction and conform evaluation. So a low credibility means a high probability of an impossible result. Why? Because when we have a low credibility, you can imagine this region where we're outputting the empty set to be quite large, and here we are saying that we're giving a large probability, again, of an impossibility, like that we're violating the closed rule assumption. So in conform evaluation, we're directly interpreting this, that we have violated the assumptions, and thus this sample is very likely to drift. So there's also a very significant difference between conform predictors and conform evaluators. So conform predictors directly predict this kind of prediction region. Conform evaluators instead use conform prediction to kind of give us some quality measure for the classifier. So we spoke about conform evaluators, but if you remember, these conform evaluators feed into Transcend, so the rejection mechanism. And the question that Transcend is trying to answer is, when is the quality of a prediction bad enough that you need to take action and actually do something about it? So the Transcend framework searches for rejection thresholds based on the difference in p-values between correct and incorrect predictions for each class. So let's have a look at how this works. So imagine you have your classes here, and since this is a training time, we know the true label, so we can make the classifier kind of predict on these classes, and we can partition them into correct and incorrect classifications. And these classifications now we're ordering by the credibility score. So this is the score assigned by the conform prediction procedure. Now, what Transcend will do is find thresholds for each class such that it's optimizing some kind of performance. So, for example, we could tell Transcend to optimize, we want to find the thresholds that optimize the F1 score given some constraint, or so that maximize the F1 score given some constraint on how many rejections we are happy to suffer. Now, at test time, what we do is we simply compute the p-value for the new test point, and then we compare it with the with the threshold for that class. And if it's above the threshold, then we keep the prediction, and if it's below the threshold, well, then what we do is we simply reject it. And then once you reject the point, there's various things one can do, so manual inspection, downstream analysis, quarantine, and so on and so forth. So let's have a look at conform evaluators more in practice, how the procedure actually kind of works. So the original kind of conform evaluator is a transductive conform evaluator. So here you can imagine this as being kind of a leave one out procedure. So we compute the p-value of the point based on like the n-1 points. So we're effectively training n classifiers and doing leave one out to compute the p-value for each point. So this is rooted in conform prediction theory, but it's often computationally infeasible. So as a first attempt to improve this, we propose the approximate transductive conform evaluator. So now instead of doing a leave one out, we are computing these p-values in batches. So you can imagine this as being some kind of a k-fold. And the issue with this is that it's actually an unsound procedure from conform prediction theory, because it's only as sound as the you can imagine that if we're doing batching now, for example, the hyperplane or the decision boundary will be an approximation now, instead of being the kind of most true decision boundary. So it's only as good as how much this this approximate decision boundary, how close it is to the original decision boundary. Because you can imagine if you have a non-conformity measure which is computed based on the decision boundary, then this non-conformity measure now will be different if we're batching. So we wanted to kind of get the soundness back, and to do this, we split our training set into a proper training set, which we train our classifier on. So this is the gray region, and then a calibration set. So now in the calibration set, we do still like a leave one out fashion, but we use the classifier trained in the gray area. So this is rooted in inductive conformal prediction theory. So this is a sound approach, a statistically sound method, and it's computationally very efficient. We only have to train one classifier, at the cost that we're being informationally inefficient, as we're throwing away a lot of like p-value computation here, or non-conformity measure computation, for example. So kind of as the grand finale, we have this cross-conform evaluator. So you can imagine now as being some kind of k-fold of ICs. So the idea is that now these gray regions, now since we're doing some kind of k-fold, now they essentially disappear, because we are now computing statistical support over the entire data set. And then we keep these k inductive conform evaluators to vote in parallel. So we have some kind of majority voting system, and this majority voting can again be kind of tuned depending on how much kind of ensemble confidence one requires. So this is a very exciting kind of direction as well. And here's the experimental setup. We wanted to be kind of as varied as possible. So we have Android experiments with Drebin, which is a state-of-the-art kind of Android malware classifier. This is a linear support vector machine with a binary feature space. Then we also have experiments on Windows portable executable malware with a gradient boosting decision tree and the Amber dataset, which is quite a popular one. Then PDF PDF malware experiments with the HEDOS dataset and random forest. So we also use some specific threshold optimization constraints. Again, these can be tuned. What's important to mention is that these threshold optimization constraints are only respected at calibration time. Once we reject or once we're at test time, these do not need to be respected, and actually we don't want them to, because we actually we hope that with more drift we'd have more rejection, for example, than the one we set at calibration time. So we'll be focusing on the Android experiments for brevity, but you can check them out in the paper for the other experiments and results. There's many. So let's have a look at how these conformal evaluators do. So to read these plots, there's the middle gray dashed line, which is the baseline performance. This is just the Drebin support vector machine if we don't do anything. So we see that as time goes on, there's more and more concept drift, and the classifier kind of decays in performance. So then we have the blue top line is the F1 of the kept elements, and the red bottom line is the F1 of rejected elements. So we want the F1 of the kept elements to be close to 1, and the F1 of the rejected elements to be close to 0, because this means we're accepting the correct classifications and rejecting the incorrect ones. You can also see in the background a histogram of the quarantine elements. So you can see that as time goes on, we have more and more rejected elements in the again, this is, you can also kind of see that there's more rejected elements when there seems to be more of a drift in the baseline. So for example, around months 25 to 28, there's a higher rejected element, or there's a higher rejected percentage, because you can see at the base there seems to be more drift in that kind of area of time. So this is approximate TCE. We also have IC, and IC, as we can see, performs very, very similarly to approximate TCE, but with kind of a much lower cost of computational cost. So CPU hours of 11 compared to 46. So this again, here we're training only support vector machines, but you can imagine if you're training some neural network model, this is actually even more significant. It's actually quite nice to see that the IC performs very, very similar to TC with the computational advantage, and then we can compare with the cross-conformal evaluation. And here, this is like we can see a different behavior now. Again, conformal evaluation is kind of an ensemble, so you imagine, or you'd expect that there will be more rejections, which we can see in the histogram, but the more rejections come at the benefit of the baseline, or as the kept F1 score, which is the blue line, which is very close to 1, but unfortunately come at the cost of the rejected elements. So there are some mistakes in the rejected elements, but again, this kind of depends on the task at hand, because perhaps you're happy to reject more elements just to make sure that all your accepted classifications are correct, or at least are likely to be correct. So you could tell me, okay, but why don't we just use classifier probabilities? And this is the reason why. So here we have the same plots as before, and under we can see the kind of, if we do the same techniques, but now instead of taking the p-values generated by the conformal evaluator, we take the probabilities generated by plot scaling. So this is a standard support vector machine technique to generate probabilities, and we can see that the probabilities, they start towards the beginning to be relatively alright, but then I mean, still perform much worse. But then as time goes on and there's more drift, they start performing pretty much randomly on the data set, and this is actually not unexpected. Actually, this is the fundamental issue is that probabilities rely on this IID assumption, but now we know that the IID assumption is being violated quite violently, and we can see this in the performance of probabilities. So this is why using this approach with conformal evaluators is useful in practice. So to summarize, we have presented an extension of Transcend rejection framework, which offers efficient and effective detection of drifting objects. And we demonstrated how we can apply it at scale in deployments. feel free to go to check out the code in the and the original Usenix paper and our paper as well. And thank you very much for listening. Bye bye.